math. Right, at least a few. So there's a fair amount of math in here, but as I'm a physicist by training, I'll try to hand wave it. So I've been interested for the last 3 years in modeling the resting brain, and in particular in estimation problems. So to give you an idea, this is the kind of data set I work with. So what you're seeing here is activation. When it's blue, it's below average. When it's yellow or rather red on your screen, it's above average. That seems a bit random fluctuations. So this is a subject sitting in the scanner to whom we've asked just to think about nothing. But if it was actually a subject doing a specific task, I don't think any one of us would see any difference by looking at this kind of movie. So this is the kind of data set I work with. So why would we want to study resting state data set? So we could be, a lot of people are actually interested in trying to learn structure in these data sets with the idea that it will reveal some intrinsic structures that are in ongoing activity. So people like to call ongoing activity not only resting state activity, but also the activity that will go on top or below of the task evoked activity. So it's present all the time. Another application, a very important one, would be can we learn diagnostic markers from this kind of data set, so in resting state. And this is extremely interesting for medical applications. And for these applications, we are going to need population level models. And by population level, I mean models that go beyond the single subject. By models, I mean models, at least I am interested in models in the statistical sense, so generative models, with an explicit statistical model of subject-to-subject variability. And these are going to be useful for, at least I'm interested in them for two specific reasons. One is that they enable us to accumulate data across subjects. And another very important reason is that they tell us how we can compare subjects. So I'll first talk a bit about what spatial modes we can learn from ongoing activity. Then I'll describe a bit how we can learn graphical models that reveal brain connectivity. And finally, I'll talk a bit about how we can detect differences in connectivity. So we've seen this random locking data set, and it's been known for quite a while that there's actually a lot of structure, spatial structure in this kind of data. This is, for instance, what's being called as the default mode. It's very structured, it's fairly reproducible across subjects. So in general, if we try to put a model on what people have been doing to estimate this structure, that's what I like to call a decomposition model. So basically taking what is better, the mouse or the pointer? Pointer, all right. So so this is our data set. It's a big chunk of data, and we're interested in decomposing it in a set of time series and a set of relevant, where relevant is an ill-defined concept, spatial maps. And of course, we're not interpreting all the data, so there is a bunch of data that we're rejecting. We're not interpreting it. We can call it noise. So typically, people have been using what's known as ICA, independent component analysis, to do this, which minimizes the mutual information between the different spatial maps S. So I'll be talking about something different than ICA, but I'd like first to review a bit ICA, especially why it works on brain data set, because it's been fairly successful across the last 10 years. So first, as I'm interested in group models, what people are actually doing is working from a set of different data sets from different subjects, and they're trying to estimate common spatial patterns. So this could be written as a set of models, but what people are really doing most of the time is concatenating them to solve this as one big model. And this, what is interesting to see here is that what people are doing is minimizing the norm of the concatenated residual. And as a group model, this corresponds, I like to call this a fixed defect model, because really it's the norm of the residual at the group level without making any difference between subjects. So the residuals are modeled as identical and independently distributed. So this has been introduced by Vince Calhoun 10 years ago and has been used a lot, very successfully. So however, so we were interested in seeing if we can go further than this, and if we look a bit at the noise model that's here, what we're doing is that we're taking the concatenated data and just minimizing the residuals here, and then afterwards running the ICA on this. And the reason is that we're doing this in a two-step is that ICA doesn't really have a noise model. So what we've tried is to add an explicit difference between noise at the subject level and noise at the group level. And so at the subject level, we use a PCA, principal component analysis. And at the group level, we use a canonical component analysis. It's fairly similar, except it forgets the variance at the subject level. So now what we have is a two-step level with rejection of observation noise at the subject level and rejection of subject-to-subject variability noise at the group level. And then we run ICA. And so we've called this approach CanlCA for canonical ICA. And so what's interesting is it actually works fairly well. It's actually a fairly interesting improvement. And one way to quantify this is to look at the reproducibility across control groups. So we have, say we have 12 subjects, and we're interested in learning patterns of resting state activity in these 12 subjects. And if we want to use these patterns as biomarkers, well, they better be stable if we believe that the subjects are similar. So what we did was to split the group in two randomly, quite a few times, learn spatial maps on the two subgroups and compare them. And so we found out that, so if we just run a PCA plus ICA, which is the standard way that is described in the literature, we find not excellent reproducibility. So 0 is completely reproducible, and 1 is completely reproducible.
What is the reproducibility measure?
So this is one-to-one matching of the maps using a correlation, spatial correlation, and we've looked at other metrics. It's actually interesting also to look at not doing one-to-one matching, so looking only at the subspace that I spanned. But at least here, what I'm showing here is one-to-one matching, because this is really what people are doing in their head. They're really trying to identify maps.
No threshold.
This, I believe, is thresholded in the paper. We looked at thresholded and not thresholded. I'll come back on the thresholding though. So what's interesting to see is, so if we just do a standard PCA plus ICA, we get not terribly reproducible. If we add the CCA that I've introduced, we get a huge gain. And if we look at the code, the software packages that people have been using, it actually sits in between. And to understand this, I had to look at the source code, and it does something that is not a CCA, but is somewhat related. So now that's the quantitative evaluation of whether the CCA actually improves. Now, if we actually look at the components that are extracted, so we extract a certain number of components. We used 42 in this study, but that really doesn't matter. What matters, and it's very qualitative observation, is that if we add CCA, if we compare maps extracted with and without CCA, we find that they're actually much more interesting in the sense that they tend much more to segment salient features like what you see here, rather than have fairly flat, uninteresting maps. This is very qualitative, but let's keep this in mind. So, and the reason the way we interpret this is really that there is subject-to-subject variability, and by modeling it, we're able to capture a better subspace. And I'll come back on this a bit later.
Sorry, one more question?
Yeah.
What coordinate system
This is all MNI, and this was realigned using SPM5, I believe.
So affine or just cosine or Dartel?
So that was back when I started doing neuroimaging, so I did not do the pre-processing myself. It's definitely not Dartel. It's probably new segments, so that's a cosine base, I believe. But that's old. I didn't understand this really well. But yeah, definitely. Oh, and something fairly important actually is that the data have been spatially smooth. So so I use the standard pipeline that is used in the cognitive science group of Neurospin, and they smooth a lot. They smooth by 6 millimeter. Actually, we can come back on this later on if you're interested.
Standard deviation or full width half?
I think full width half maximum. I believe. All right, so let's put this aside a bit and look at a bit what we interpret in these maps. And really what we interpret are the salient features that you see here. So this is what's called the default mode. And really what people are interpreting is this. If you talk to practitioners, they're looking at this. And so if you have a map like this, which does come up in the studies, they interpret like noise, nothing interesting. So really what I believe people are interpreting are the blobs, we like to call them blobs, standing out. And the background is called noise. So if we look at the marginal distributions of these maps, we can see that there is a big central mode, which is really the background here and here. That's mainly the distribution, and there are long tails sticking out. And what ICA has done, and this is really what ICA does, is to select for these long tails. And so now we're selecting for these long tails, but we're really not interpreting the background. So what we did is to make a model that simply says, well, this background is noise. This is not what we're interested in, and it's only the tail that we're interested in. The interesting part is the long tail distribution, and the background noise is an isotropic central mode. So what this leads us to doing is simply actually thresholding with a given threshold that can be computed to recover what we're interested in. And the nice thing is that using this thresholds just thresholds out the non-interesting signal. But what's really interesting is that if we try to put a model on this, and it's actually fairly easy and fairly natural, a simple model that we can put is that the interesting sources that we're selecting for are sparse, and that we have additive Gaussian noise to it. To these sources, and in this context, thresholding the ICA is actually a sparse recovery procedure. So I'd like to say that we validated this by comparing to other thresholding procedures, for instance, used by Melodic, that there's a mixture model. And the way we validated this was by taking a data set with a lot of data and removing data from it and seeing if it were more consistent or less consistent.
Sorry.
Sure. No, I like questions.
When you say it's sparse, are you saying that there are few vectors in S, or are you saying that there are few non-zero elements?
There are few non-zero elements. There are few. Really, what we're interested in, at least this is my claim. I'm not the only one to make this claim. Ingrid Debeshi did it in a PNA's paper. What we're really interested in is this map, and this map is mostly zero and has a few activated. And I'll come back to this because at least I believe this is really what we're interested in, and we're not interested in. Well, we're not really interested in minimizing mutual information, and absolutely not interested in independence, even though we're using ICA. All right, so now if we have a look, I'd like to have a little look at the maps that this procedure selects. And I've displayed them here. So this is maps of the visual system, and you probably can't see them, but you can see them on this snazzy 3D picture. And this is maps of the motor system. These are more frontal structures. And if we look at, if we put them all together, what we really have is some kind of brain parcellation. So ICA, when it's tuned a bit to work on brain data, extracts almost a full brain parcellation. And I think this is one reason why it's useful. However, I must confess I don't like ICA. I've moved away from it. And the reason is that we have no overall control of the residuals. What we've done here is successful estimation, applying one model after the other, and each time you're throwing out data. There's no overall control, but really what bothers me most is it does not select for what we interpret. It selects for a minimal mutual information, and we're really not interpreting this. We're really interpreting blobs. So any questions on ICA? All right, so then I'll move along to what we've been doing more recently is we've just taken a very similar generative model than the one in CanlCA, just changed it a tiny bit. And so what we're saying is that we have we're observing a product of time series and interesting relevant subject maps, and these subject maps are really derived from group level maps. And so we write the equations. This equation is really saying that is really this one product of time series and subject map plus noise, and then we say that the subject maps are really group level maps plus subject to subject variability. And then, so this is slightly different from the CanlCA model, but not really. And then we depart from the ICA model, and what we're saying is really the group level maps are not independent, they're really sparse. And we had to add a bit more. We had to add that they were also smooth spatially. And so this can be really written as a prior on the group level maps. The nice thing is that then we can do, this is a well-posed statistical model. And the problem with ICA is that if we try to write it like this, ICA is actually an improper prior. So we can write it like this, but we can't estimate it like this. And then we can do maximum and posteriori estimation. So this is really writing the likelihood of this model that looks like this, and it's really made of a data fit term, a subject-to-subject variability term, and a prior term that appears as a penalization that selects for sparse and smooth maps at the subject level, and then we can write an optimization algorithm for this. And as I think some people here don't like math, I'm not going to go over the optimization algorithm. However, I'd like to point out that what is really interesting here is that we can work with a full data set. If we have 20 subjects, we don't have to do estimation of each subject one after the other. We can throw this on a big computer, wait a little while, and we can use the full data set to estimate the group level map. This is the good thing because we can fish all the interesting information. The bad thing is that it's actually fairly computational intensive. We're going to put a data set that is a few gigs in RAM, and we're going to try to optimize a nasty optimization problem on it. So this problem is actually chosen so that it brings up some fairly fast to optimize subproblems. In particular, at the group level, there is what's called a proximal operator that appears. And this is a very well-known operator in image denoising. So it's not obvious, but we're actually grabbing some results from the image denoising literature and sticking them in here. All right, so parameter selection, I won't go too much. Well, I'll skip it. But just to say that we're not, selecting mu and lambda just to make the maps look good. We actually have procedures to select them. At the end of the day, what we get is a set of maps at the group level. I've displayed the outlines here. But what's really interesting is that we're estimating jointly a set of maps at the individual level. And I'm not sure you can see here. So what I've displayed in black and white is the posterior probability of gray matter as segmented by SPM of each subject. Here we have two subjects. In pink, that you can probably not see, is the outline of the group level map. And in yellow, that you can probably see, is the outline of the subject-specific map. And these maps and the subject-specific maps were estimated only from the API. They've never seen the anatomy, even though, of course, there is shared information. And what's interesting is to see that the individual maps follow the gray matter much more than the group level maps. So this comforts us that we're probably really estimating subject-to-subject variability. We also have simulations in which we put in simulated spatial variability and we recover it, and it works also on the simulations. But I'm more comforted by this. So if we compare this to ICA, what we see is that ICA is much more noisy. It gives similar results, but it's much more noisy. And the way I interpret this is that the criteria that we're using to select noise, observation noise at the subject level, or subject variability noise, is really not informed by our final goal, which is to have sparsity. I also should say that the ICA has no spatial model, so we need to smooth it. Here we don't need to smooth it because the smoothing is in the penalization. Where is it? Here. Just our penalization is we're doing smoothing as the prior rather than smoothing the data. All right. So also, if we look at the raw map, so here I'm displaying a non-thresholded map. What is transparent is really where it is really zero. I don't have to threshold this. And here I'm displaying a non-thresholded ICA map. And so what we have here is a much higher contrast, obviously, because we've selected for sparse map. And it's actually much easier to segment structures from such a map than from this one. And finally, because of all this, we're able to segment some deep structures. This is a bunch of basal ganglia that stand out fairly well, and they really don't, at least on this data set, they really don't stand out this way with other methods. I should stress that the multi-subject step is important, improves a lot. If we just do some kind of sparse PCA on the data set, it doesn't work as well. So of course you can always find more details. These have been published as a conference paper where you'll find more details. All right, so what we've been looking at really is the spatial modes here, and by choosing the right prior, we see that we can make these spatial modes really look like a parcellation of the brain. So really we've gone from these unstructured fluctuations to a brain parcellation with a fairly simple model, actually. What I'd like to focus on right now is the associated time series, and in particular, I'd like to look at the correlations between these time series. The reason being that, this is really a correlation, we can look at it as a correlation matrix, and it has actually a lot of structure that displays a known structure in your science, such as the default mode, but we can look at it as a graph, and this is also I find at least very interesting, and it's done a lot in neuroscience nowadays. So just a bit of a graphical model from correlation structures. So we can write this as the simplest possible model, which is a multivariate normal, and it's parameterized by the inverse covariance of our model. And so if we look at the covariance matrix, so this is a very simple example. The covariance matrix is fairly full. It's a fairly full graph if we look at the associated graph. But the inverse covariance gives us partial correlations. It gives us conditional relationships between the nodes, and as a result, it's much sparser. It's the effect of this node on this node conditioning out all the others, whereas this is not conditioned. So we're actually really going to be looking at inverse covariance. Now this is, if people are interested in statistics, this is pretty much the framework of Gaussian graphical modeling. So to estimate these, so we're really interested in estimating the inverse covariance. And so once again, we're going to estimate it in a maximum posteriori framework, so just maximizing the likelihood of the model plus the penalization. And it's fairly standard to use a sparsity-inducing penalization. So really, it corresponds to the prior that many pairs of regions are actually not connected. So we're going to put a prior that pushes connections to zero, and it gives a Lasso-like problem, so an L1 penalization for covariance estimation. So this is fairly standard and done a lot in statistics. So what we've done with Alex Gael, who's sitting in the room right now, is to introduce a new prior, which is really to acknowledge the fact that we have several subjects, and these subjects, they share information across the different graphs. which is the prior that we've used is that they have the same independent structure between regions, but they might have different connection strength. And so what we're going to do is that we're going to estimate together a family of inverse covariance models, or a family of graphs using penalization that is corresponding to what's known as the group-Lasso problem in machine learning, and it's what known as an L2-1 penalization. Here's the formula if you're interested, but I see that people are running away, so I'll skip. Now, one important thing though is that it's a convex optimization problem, so from an estimation point of view, it's well posed. So we try to validate this on the data, and as often with fMRI, it's always really hard to validate. But let me try and convince you that this actually works and is useful. So this is the empirical inverse covariance. So just empirical. So maximum likelihood estimate, not regularized. It's not really sparse. So this is the sparsity pattern. We could threshold it, but there's a lot of background. If we use a standard sparse inverse covariance, we find much sparser graph, and I could display the graphs, but they would be fairly black. You wouldn't see much. And if we use our population prior, we find even sparser. So it's not sure whether this is good or bad. So we can look at the likelihood of new data. So we leave out data and try to see if it fits our model. And we can see that basically maximum likelihood estimate really doesn't work well. And this is of no surprise. The reason being that we don't have much samples to estimate these graphs. If we had plenty, it would work really well, but we actually have something like 200 observations per subject. With single subject data, a sparse inverse covariance works really well. We have a huge gain. Now, if we take the group data and we pull the group data together, we see that it does actually much better than the single subject maximum likelihood. But if we use the maximum likelihood, it doesn't do as good as the well-penalized single subject. And the reason is that we're really learning an average group model. We're not learning something that is specific to the subject we're interested in. So at the subject level, we don't have enough data. At the group level, we've got plenty of data, but we're really learning an average. And so, if we try to penalize the group level, we don't gain much. And so if we use our population, what we call our population prior, that allows to combine across subjects without forcing the subjects to be similar, we get some gain, a decent gain. So this is why we think this is better. Now, if we look at the graph, it looks like this. So this is just a raw graph. Maximum likelihood estimate is just full, black, can't see anything. This is the graph that we get with the population prior. It looks very structured. If you look at it in 3D and try to understand it, you feel like there's something in it. But how can we quantify this? So what we did is we looked at what people are trying to find in these graphs, there is something that people look a lot at as what's called functional segregation of different brain regions, so that brain regions will group together to answer specific functional need, a functional role. And there's a measure that's being proposed for this, which is called modularity. So basically, we're dividing the graph here in a set of communities. So we use the convex relaxation of the problem. I'm not going to go into this. And at the end of the day, we run the algorithm, and we find the communities here. I've displayed all the different communities with different symbols. And so on this graph, the communities really match what's been known as large delocalized resting state networks. Whereas on the raw correlations, there is very little structure. So this makes us believe that not only does the model generalize better to new data, but also it captures better some neuroscientific truth below this. All right, I'll just skip this. So, any questions on this, by the way? No. So what we have right now is that we've been mapping at the level of the full brain. We've been mapping a fairly large graph of functional connections. And if you go to find a neurologist and talk with him, he says, well, this is really interesting because there are some pathologies, for instance, stroke, which we believe are going to impact these functional connections. And strokes are especially interested, and I've been paid by a stroke study for the last year. So, because if you have a lesion that has damaged anatomically tissue in some area, what you're really interested in is to know whether there is some functional damage that in anatomically non-damaged areas that are distant from the lesion. And one way that it might be interesting to detect this is using resting state data sets. So can we use ongoing activity or resting state data sets to do a prognosis of stroke recovery? And some people really believe that we can do this. So to be able to do this, we need to be able to detect differences in connectivity. And I thought this was actually really easy, but if you look at the data, these are the correlation matrices of different control, and this is the correlation matrix of a subject that has a large lesion. So can you see where the lesion is? I can, because I've been staring at this data for a long time, but it's really not obvious. And the reason is that there is a huge amount of variability across the subject that is spread across the correlation matrices. It's not localized. It's not white noise. What this tells us is that we cannot apply univariate statistics. So we cannot, just take a control, take a patient, subtract the two, and do statistics on this. From a mathematical perspective, if we do this, we're immediately going to run into problems because we're going to find non-positive definite correlation matrices, and these will describe impossible observations because they have negative variance. And really, the reason that we fall in these problems is that Gaussian models, the correlation matrices that parameterize Gaussian models, do not live in a vector space. We can't do linear models with them. So to get a bit of an intuition of the problem, we did a few simulations. And here we're simulating two different graphs with just a tiny difference between the two on the inverse covariance. And this is the difference on the covariance. So the difference on the inverse covariance may be well localized. It's only one edge that's been modified. On the covariance, it's spread out all over. All right, so when I saw this, I thought immediately, well, we need to do the statistics on the inverse covariance, not on the covariance. So now if we look at the estimation noise on the inverse covariance, it's extremely non-homogeneous, and it's actually here. I took the example where it's biggest, where we modified the link, but in general, it's biggest in more integrated regions. Whereas it's more homogeneous, but also inhomogeneous on the covariance. And so what this tells us is that we really have an estimation problem, because on the one hand we have non-local effect, on the other hand we have non-homogeneous noise. So if we try to do this as linear models and independent statistics, we're really going to be detecting remote effects that are only due to the non-local effects. All right, I'm gonna breeze through this, but just to tell you that I'm doing a bit of hand waving here. There is actual math behind this. There are really fancy math that tells you that we know the shape of the error, of the estimation error on these covariance matrices. We know this from statistical principles, and it's actually, it really depends on the covariance matrix. A different covariance matrix will give you a different shape of error. We can use this knowledge to parameterize so the covariance matrix sits on a manifold, and we can use this knowledge of the error to parameterize the manifold. And really what we're doing is a reparametrization. Okay, so this is the math. What we're doing is a reparametrization to work on a tangent space, so a flat space, where the error, do I have this? Yeah. The error are actually all isotropic. So here, the problem that we have is that each covariance matrix has a different estimation error. It's got it has a different estimation error, and I need to acknowledge this when I do the statistics. Whereas if I work in the tangent space, they all have, at least in this tangent space, locally, a similar isotropic independent estimation error. And so what this tells me is that I can do on the tangent space, as long as the subjects are not too different, I can do a standard univariate statistics on this. So brain mapping like statistics. So blah, blah, blah. I'm trying to skip the math. Right. So one thing it does tells us also is that we can build a principled, well-behaved likelihood for the variability of these covariance matrix, and this will be useful. I'll come back to this, but this will be useful. But really, what was driving me is that using all these math and the model, which is, it's actually the simplest model, the less informative model that you can think of on covariance matrices. With the parametrization in the tangent space, under the null hypothesis that a subject is in the group model, we find that our parametrization is independently distributed. Therefore, we can do univariate statistics, and so we apply. So we really apply things like non-parametric statistics on them. And so right now, I'll jump to some experimental results on strokes, and I'd like to stress that so the data and all the medical knowledge has been gathered by Flore Baronnet, who's a medical doctor I work with, and this has been really, the project has been supervised by Anders Kleinschmidt. So we have, this was a preliminary data set. We had 20 controls and 10 stroke patients. And really the challenge with these patients is that they're all different. They all have lesions in different areas. They all have different symptoms, and you can't really just bend them together, do an average, and do statistics on this. You can't. You have to consider each patient differently. So now, if we look at the likelihood of our model, this is the likelihood of a naive model, the simplest one that one could think of without doing math and manifolds and all this, and it really doesn't separate the two groups really well. Now, if we look at our model in the tangent space, it separates the two groups better, not perfectly. These patients are extremely inhomogeneous, but it does separate them better. What does it work? So these are the correlation matrices. This is what I call the residual, which is what we do the statistics on. It's just a transformation from here to here. You can see that for controls, really, this is pretty much white noise. The projector doesn't allow you to see this, but there is a bit of fluctuation here, but it's white noise. We've decorrelated this correlated variation. Whereas here, we have a few areas that stick out. And this is where we can do our detections. So by the way, this guy has a lesion here, and these are probably remote modifications of the functional structure. So across our patients, if we look at the number of detections that we have, we find that, so this is doing non-parametric statistics, so we're probably conservative, and we're Bonferroni corrected, so we're probably conservative. So we have systematically more detections of differences if we work in the tangent space than if we do univariate statistics on the raw observations. And if we go in and we try to have a look at what we detect, well, on some patients, this is a patient that has a lesion here, and we're really detecting that the connections directly to the lesions are modified. So this is not surprising. Actually, sometimes patients have lesions and we can't detect this, and this is probably because they move too much in the scanner or acquisition. Yeah.
Can you go 2 slides up? So what regions or what do we see on the axis here? How many regions did you get? How did you define them? Or and probably 2 slides further. So are these all? Is this everything you put into it or something?
Yeah. So I'm changing a bit because it's a really hard problem. Before, I was showing you things with a huge amount of regions, 150 regions. Here I'm showing you results with 30 regions. The reason being that the more regions we put in, the higher the statistical problem is going to be. So we really, our long-term goal is to be able to put more regions, to be able to detect finer modifications, but currently we're not able to do this. So we've been hand defining them with Andreas and Flor, and it's been a terribly lengthy process, and it's also really guiding my research on the spatial mode, because hand defining does work, but it's really not getting anywhere in the long term. And it's not, so I'm exaggerating. We're not hand defining them. We're using coordinate from the literature to do seed-based analysis, and with the seed-based analysis, we're across the groups, we're really taking the peaks of the seed-based analysis. But I don't think this is getting anywhere, and we found that we have to be really careful with the definition of these regions.
How many regions?
33 here, and I think this has evolved across time. I think we're up to 36 because we're trying to find specific problems with language network, or but yeah, I'm not happy with hand defining, or at least playing with the parameters to define the regions. But right now, with the current state of the spatial models, we're not able to find regions that will work out of the box. We have to tune them a bit.
You could use your generative model that we talked about in the first episode to define your regions.
That's the goal. I should say that this is actually anterior to our multi-subject dictionary learning, or that's the goal. But even though I think right now the multi-subject dictionary learning is still too noisy, we have ideas how we can modify it, but right now it wouldn't. I don't think it would work out of the box. What would work, I think, is to take the output of the dictionary learning algorithm, to correct it manually, to remove some noise, to remove some uninteresting features, and then to use it. I think that would work. I'd like to move away from this. All right, so this is actually a much more interesting example. So this guy has a lesion on the visual system on one side, and we can see that connections to the visual systems are damaged. What's really interesting is that we can see that on the other side, there's actually modifications to the other visual system. And this is the kind of things that we would like to detect. So the fact that if I modify anatomically some part of the brain, I will have some functional modifications in distance.
Is red strengthening and blue weakening?
That it's the case. I wouldn't overinterpret these results. I mean, what we see here is really nice. This is what we're looking for. However, we have very few, at least in this study, we had very few patients. Now we're working with 200 patients, but what we find is that we need to be careful about registration effects of the lesions and these kinds of things. So we don't have results we can claim are neuroscientifically significant right now. Hopefully soon. All right. With that, I'd like to end. I'll put the thanks slide before the conclusion so I don't forget. So yes, I've been working with Bertrand Thirion and JB Pauline for the modeling. Andreas Kleinschmidt has really been giving all the knowledge of ongoing activity. I've been working with many other people for the different models. There's actually a lot of model building. When we ask this question, we're trying to exclude people who have lesions in a language-related area, because it would make sense that there is an asymmetry. And so we're not sure we have a p-value on this statement right now.
So I have a question actually. Have you looked at structural connectivity and see how these layer maps that you showed, like the stroke patients, would overlap with the structural connectivity?
So on the stroke patient, we haven't looked at. It's actually something. I mean, I've looked at with my bare eyes, and looking at when a lesion was located in one of the main tracts, and it seems that there is a lot of looking with my bare eyes, but we've not done the math. It's actually really hard to get p-values on stroke patients, so I'd like to get p-values without anatomical connectivity before we move on to p-values with. But it's a very interesting problem.
Yeah,
tuer, je fais toujours trop de maths, moi. Alex m'avait dit, fais gaffe.